Hello, everybody. Today's lecture is one of our pre-recorded lectures, and this is one that is going to cover a topic that you're going to want to spend a little bit of time on. We'll do a little bit of review. We'll talk about some of the stuff that we've previously talked about, just a little. Um, but this is more organic chemistry. Now, if you remember last time when we were talking about organic chemistry, we were talking about applying names, and we were talking about basically a more or less nomenclature, naming. So we're going to take naming and now we're going to apply some new things to it. And the new things that we're going to apply are commonly known as functional groups. Now, if you look over on the left-hand side, you're going to see a bunch of functional groups. Now, what we've done so far is we've talked about these first three: alkanes, alkenes, and alkynes. So, functional group for an alkane, there is none. The reason for that is an alkane is nothing but single bonds. Alkenes, however, well, that's where we have a double bond, a carbon-carbon double bond. And here is our depiction of that functional group. Last are our alkynes, where we have a carbon-carbon triple bond. Now, what else is bonded to those carbons? It's highly variable. So this right here. This is an alkyne. It's 4 carbons. 2 of them have a triple bond, and then 2 of them are singly bonded, or 2 of them have a carbon-carbon triple bond. Then the other 2 carbons are singly bound to each of these 2 carbons. Now, I think that if you wanted to look at like the simplest possible molecule or the simplest possible alkyne, excuse me, it would look like this. Now, my point in bringing all of this up is that if there's something that I want you to kind of think about as maybe prioritizing, I would definitely get my nomenclature with respect to alkanes, alkenes, and alkynes like solid and strong, and then feel more comfortable to work on functional groups, other functional groups. Now, in this lecture, we're going to go through a couple, and then the next lecture, we're going to go through a couple more. Overall, there's also alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, amines, and amides. All of these are very important, and arguably, all of these are I would say that these are, simply put, the most important biological functional groups. Now, what functional groups do is they basically give a molecule a unique function. Now, organic compounds, we can use organic compounds to be categorized by the functional groups that are found in a given molecule. Now, when it comes to functional groups, back here, these are your primary things. These are the big ones. There are other functional groups. So here, one way to look at it is functional groups, the main players. The main players are your alkanes, alkenes, alkynes, alcohols, ethers, amines, or amines, sorry, alkyl halides, thiols, amides, carboxylic acids, esters, ketones, aldehydes, and benzene rings or phenol groups. Now, I kind of did those out of order, and what I was trying to do is really mention them in the same sequence that they were on this page. Now, this page includes a couple fewer, or a fewer number than what are shown here as the main players, but this wasn't really intended to be a super comprehensive list. These are just kind of prioritizing, or this prioritizes biologically relevant. Um, and so since we're talking about drug design, functional groups that are important for drug design. Now, there are other functional groups that we'll simply refer to as the supporting actors. There's nitrile, just like nitrile gloves. You know, if you ever go into a biology lab or a chemistry lab, you'll have to put gloves on. And those gloves are either latex or what lots of people are using are nitrile gloves because there's lots of people who have allergies to latex. They don't have the same allergies to nitrile gloves. There's epoxides, disulfides, imines, acid chlorides, anhydrides, nitro, and sulfide. These are other functional groups. Now, again, you do not have to commit these to memory. What I want you to know is I want you to know the ones that we talk about and kind of highlight and we go after specifically. So with that in mind, let's go back and talk about our alkenes again. And this is essentially the same slide that we saw previously with respect to with respect to alkenes. However, I want to bring this up because one super important thing to know about alkenes is that they undergo something known as isomerism, or they exist as what are known as isomers. So here's the thing with understanding isomers. If you look at this molecule right here, and this molecule right here, if you dissect it for a second, what I want you to see is that here is your double bond. Here's a double bond. Okay, now let's look to the left of that double bond. When you look to the left of that double bond, I'm going to erase my circles now. In both molecules on the left-hand side, you'll see the CH3 is, I'm going to describe it as up or on the top of my molecule. It's on the, it's above my double bond. Okay. Now let's go back to our double bond. Okay, we're living right here, here. Let's look to the right of our double bond. Now, in the molecule on the left, which I'm going to label as L for left and the molecule R for right, what you'll notice is that CH3 in the molecule on the left-hand side, well, that's CH3 on the right-hand side is up, okay? So in our molecule that's shown on the left, I think it'd be fair to say that both of these CH3s are on the same side of my double bond. They're both on the top half of my double bond, okay? Now, if we look at my molecule on the right, then we've got CH3 on the left, that's up, and a CH3 on the right, that's down. Now, these two molecules, these are known as isomers. They're known as isomers because they are different. Now, this is a little bit tricky to wrap your mind around because if we write out the chemical formula for each one of these molecules, I'm going to look on the left-hand side and I'm going to write out the chemical formula for the left-hand side. I've got CH3. Then I've got C, and that is going to one bond or one hydrogen. So that's accounted for. Then I've got this carbon, this hydrogen, and then CH3. Okay. If I look at the molecule on the right-hand side, that would be CH3, CH, CH, and then again, CH3. Okay, when we look at these two, the formulas down here and here respectively, well, they're identical. So what these two molecules have is they have identical compositions, the same, they're both 4 carbons. they both have a total of 8 hydrogens. So they're both 4-carbon, 8-hydrogen containing molecules. But where they differ from one another is the positions of these CH3s. We've got on the left-hand side, CH3 up, and then another one up. They're both up, down, opposite. I'm going to write same, opposite. Now, this is an important distinction because these result in 2 forms of this molecule. Now, these 2 forms are known as, or these 2 forms are commonly referred to with a prefix. So the one on the left, I'm going to erase all this. I'm going to leave the word opposite, then I'm going to write the word same again. So in order to emphasize that these 2 CH3s are on the same side, we use CIS, indicating same. So cis would be the same. 2, well, where is our double bond? That's at carbon number. Well, this would be 1, 2, 3, 4. Cis 2. Bute indicates 4 carbons. ENE, this is butene. Okay. Now, think about the word cis and try to think about what is the term that indicates the opposite of that. Well, it's also the opposite, so we're indicating the opposite. We're also indicating that these groups are on the opposite sides of one another. Let's go ahead and work backwards. Is this molecule on the right-hand side, is it butene? Yeah, it is. Where is my double bond? Well, it's at carbon number 2. That's the lowest possible number that I could assign. And this is one where whether I'm starting from here, 1, 2, 3, oh, oopsies, 3, 4, or if I were to start my numbering here and say this is 1, 2, 3, 4, where does my double bond start? Regardless of where I start my numbering, it starts at carbon number 2. So I'd say 2 butene. Now, are these 2 groups, CH3, are they on the same side of my double bond? No, they're on opposite. So that's where we refer to this molecule as the trans isomer. They are opposite of one another. So there's our depiction of it. So isomers are molecules that have the exact same chemical formula, but they vary in positioning of groups. So these are known as cis-trans isomers. Now, being able to identify a cis isomer is something that I expect you to be able to do. You find where the double bond is in the case of butene or pentene or any ene. So if we were to draw something like this, CH3, CH2, CH2, CH3, H. Okay. Now, for this, I want you to be able to say, is this the molecule the trans or the cis isomer? Well, in order to answer that, you have to look at where your double bond is. And then you have to look at, well, I don't care about the hydrogens, I care about other groups. This versus this. Are those 2 groups on opposite sides of that double bond? They are. Since they're on opposite sides of the double bond, this is a trans isomer. Okay. Now, what would our name for this molecule be? We've got 1, 2, 3, 4, 5, 6. So it's 6 carbons long. I'm going to go ahead and put my name together, and I'm going to say it's a trans, and I'm going to stop there. Then I'm going to go to the kind of work from the end of my name up. I'm going to say this is ENE. It's 6 carbons. What do we know about a 6-carbon molecule? Well, it is hexene. But then, as it is hexene, well, where's my double bond? And now a great question to ask is, do I start my numbering from the right-hand side of my molecule or the left-hand side of my molecule? Well, think less about where do I start my numbering and more about what's my goal with my numbering. My goal with my numbering is to give my double bond the lowest possible number. So thinking about that, if I start numbering right here, what is the number that's assigned to my double bond? Let's say this is carbon 1, 2, 3, 4, 5, 6. So this would be trans 4 hexene. Okay. So that's because I started from the right. Now if I start from the left, and those are my two options. 1, 2, 3, 4, 5, 6. Okay, here it would be trans 2 hexene. I want this molecule to be trans 2 hexene because that gets my double bond the lowest possible number, a 2 as opposed to a 4. Okay, so trans versus cis isomers, where are the groups relative to that double bond? You need to be able to do that sort of thing. And so if I give you the structure of a molecule, can you name it? If I give you the name of a molecule, can you pick out that structure? Those are important things that I want you to be able to do. Now, next, we actually kind of talked about these as well. Our cyclic hydrocarbons. Our cyclic hydrocarbons, well, we just give that cyclo stem, or cyclo plus the stem is at 6 carbons, 5 carbons, 9 carbons. And then you add ANE or YNE or ENE. You add ANE if there's nothing but single bonds. ENE if there's at least one double bond. YNE if there's at least one triple bond. Cyclopentane right here. Cyclohexane right here. Cyclohexene right here. Now, these are all the names below, or these are all the common structures that I could entertain for you. So being able to identify these structures. Now, this is important, but one of the things that's a little bit tricky about this is that whenever we're thinking about a molecule, one of the things that we're very interested in is what does it look like in 3 dimensions? Like, what does this molecule actually look like? Because if you, let's take cyclobutane here. I'm going to draw a little star there. Cyclobutane, this is a molecule that's carbon, 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 and then let's see, that'd be a hydrogen, 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 because we know that carbon likes to have a total of 4 bonds to it. Boom, 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 boom. Okay, so there is cyclobutane. 4 carbons, 8 hydrogens. Now, when you think about, or whenever I think about structures like this, I always think about video games. And the reason I think about video games is because I think about when I was a kid. When I was a kid, we had a regular Nintendo. And in a regular Nintendo, You watched Mario run from one side of the screen to the other. Mario was like flat just because the screen was flat. You never got to see like Mario from behind as he's running around. And so you were left with two dimensions. We didn't have three dimensions in those pictures or in those video games. So this depiction right here of cyclobutane, well, let me ask you this. Is this hydrogen right here? Is that in the background or the foreground, or is it in the same plane as this carbon, and then this carbon, and this carbon, and this carbon? Well, you don't really have that answer. You don't have that answer from this picture because we're kind of oversimplifying things. And the answer to this is no, they're not in the exact same plane. The reason for that is because molecules, just like life, well, they live in three dimensions. Like the way that I'm holding my hand right now, my nose is, or my thumb is closer to my nose than my pinky is because my pinky is back. It's closer to the camera. It's farther from my face. That's how molecules exist. They exist in three dimensions. Now, in order to respond to that and to depict something that's a little bit more realistic, organic chemists came together with, or came up with an idea of what's known as a chair conformation. And this chair conformation is intended to show what a molecule like cyclohexane actually looks like. You know, for instance, if we have this carbon, I'm going to label it 1, 2, 3, 4, 5, 6. Now I'm going to label this chair conformation 1, 2, 3, 4, 5, 6. This shows a more realistic idea of how far all of the individual atoms are from one another. And this chair conformation can interconvert between this structure right here and this similar but slightly different structure right here. This undergoes what's known as a chair flip to adopt this new structure. Now, let me tell you, I'm not going to expect you to draw a chair conformation, but I want you to know what a chair flip is. I want you to also know that the chair conformation is adopted to basically avoid an unstable structure. So this gives us a better sense of where individual atoms in a structure are in 3D. Now, another group of compounds are known as aromatic compounds. These are cyclic molecules, but what's tricky about them is they have alternating double bonds. So here what we have is, let's call this model A and this model B. And here what we've got is, okay, well, let's think about terminology here. Would this be an ANE or ENE or a YNE? Well, it's not going to be an ANE, or considering that there's no triple bond, it's not going to be a YNE. This is going to be an ENE. Now, this molecule is known as benzene. I'm going to label this A, B, and C, in fact. And the reason that I'm including A, B, and C, looking at all of these different molecules, is because they are all depictions of benzene. Benzene is a compound that is very hazardous. I believe it's recognized as a carcinogen, so it's a cancer-causing agent. Now, between structures A, B, and C, let's go ahead and, I always like to think about this almost like the face of a clock. We've got our 12 o'clock position, we got the 6, and we just kind of go in this direction. Okay. So I've got a double bond between carbons 1, 2, 3, 4, 5, 6. I'm going to label this as 1, 2, 3, 4, 5, and 6. Okay. In model A, I've got a double bond between carbons 1 and 6. Got a double bond between 2 and 3. And then I've got a double bond between carbons 4 and 5. Okay. So I'm going to compare that to model B. Well, here I've got a double bond between 1 and 2, 3 and 4, 5 and 6. Now, what if I were to tell you that model A and B are the exact same molecule? That's a fair and true statement. The reason is because the double bonds that are between, like if we look at model A, we see a double bond between carbons 1 and 6, and then 2 and 3, and 4 and 5. Well, those double bonds are not there permanently because electrons are being shared. This is a, we gotta erase that. Erase that. There we go. Okay, there. I'll erase A and B. Let's see. When electrons are being shared between atoms, what that means is that electrons will, let's go ahead and say that this is where a carbon is, and this is where a carbon is. We're going to share electrons, and those electrons kind of go back and forth. Electrons are in constant movement. And sometimes what will happen is electrons will get super close to this carbon right here. And they'll just kind of end up on this side of that carbon. And then what they'll do is basically be shared between these. Well, then that means that the electrons that are shared right here will basically get pushed over here. By those electrons being pushed over here, then these electrons will get pushed over here. So there's this constant movement. So it's really a fair thing to say, or it's a really good and fair thing to do, to look at these different structures and say, well, model A transitions to model B. And then to ask the question of, well, which one is right, A or B? And the answer is, it's actually both of them that are right. Because those electrons that are between the different carbons in model A are then going to be between the different carbons in model B. Now, that's a lot to explain. And if you're looking to draw this structure, it's kind of a nuisance, and it's kind of annoying to be like, oh, well, you want me to draw benzene? Well, I got to draw this model, and I've also got to draw this model. To avoid that, what people do is they just draw this model right here. We've got our 6-pointed structure, and then what we have is this simple circle in the middle to show that there are electrons between all of the different atoms. Sometimes they're between one set of two, and then another time they're set between a different set of 2 electrons. So this right here is your most accurate structure of benzene, not A or B. Now, A and B are not wrong, but if you wanted a simple, direct, correct structure of benzene, you want to draw the one that's on the right-hand side, or you want to pick the one that's on the right-hand side. So my point in all of this is that if someone were to say, this is the 100% right structure of benzene, it never changes, That would be an incorrect statement because the electrons that are shared between atoms are in constant motion. And so they're never stuck between these two atoms because they kind of jump around. They go from here, that causes these to go here, causes these to go here, which gives us this structure. All right. Now, there are other examples of aromatic compounds. There's lots of different examples of aromatic compounds, in fact. If you're familiar with DNA and RNA, then this structure and this structure are both extremely important structures for DNA and RNA. And these are kind of the foundation of DNA and RNA. Now we'll talk about those more in the future. One of the things that I think is worth noting is you've got a nitrogen in each one of those rings. And these are both aromatic compounds. Now, the other aromatic compounds that are shown here have lots of industrial applications. And we'll get to some of these other aromatics at a later date when we talk about DNA and RNA structure. Okay. Another class of, or another functional group are halogenated hydrocarbons. These are commonly known as, or also known as, organic halides. Organic compounds with halogens as substituents, those halogens F, Cl, Br, and I. What you do is you take the name and replace IDE, so like fluoride. What we're going to do is we're going to drop IDE. And we'll say, where is that? And then we'll say butane. Fluorobutane. Now that's part of the answer, but what we want to do is we want to identify where that fluorine is. So we'd say 1-fluorobutane. And then you'd be able to look at that molecule. I'm going to cook it up real quick. Butane, 1, 2, 3, 4. CH3, CH2, H2, and then this is going to be H2F. 1-fluorobutane. Now, iodopropane, 2-iodopropane shown here. Well, let's look at this. This is a little bit tricky when you first look at it, but then what you have to remember is this is 1, 2, 3 carbons. The lowest possible number that your iodine could be on is carbon number 2. Hence 2-iodopropane. Prop with 3 carbons. Tetrafluoromethane. Okay, to dissect this, tetra. Tetra indicates 4. Tetrafluoro, 4 fluorines. Methane. Okay, methane is, if we didn't have this, methane is CH3. Well, or CH4, sorry. CH4. Well, tetrafluoromethane, well, you don't have any hydrogens. Instead, you have F4. Tetrafluoromethane. That is that structure. 2-bromohexane. 1, 2, 3, 4, 5, 6. I don't even have to really entertain numbering from the right-hand side of my structure because, well, 2 is my lowest number. I can see that my bromine is on the left-hand side of my molecule. And that's going to get me my lowest possible number, hence 2-bromohexane. Dichloromethane, again, methane is CH4. Dichloro, well, that means we're going to drop 2 of them. So we'll say CH2, Cl2, 2 or dichloromethane. We don't number this because the only carbon that the chlorines could be on is carbon number 1 because it's methane. Now, chlorinated hydrocarbons, these molecules are slightly polar. They do not dissolve well in water, but they dissolve well in fats. Now, this lack of polarity allows molecules like chloroform, commonly known as trichloromethane, to, cross something known as the blood-brain barrier. So I'll underline that. This lack of polarity, or this relatively low polarity, allows that. And that's how this works as an anesthetic, and how it works, how it's so effective as basically a drug. Now, what this also causes is that the molecules will remain in the fats of mammalian cells and promote toxicity within the body. So these molecules basically get in and they get into the fat. And that fat's not necessarily going to be removed very quickly. So they'll stay there and they can continue to cause problems or do what they do, which is potentially hazardous. Now, chloroform causes toxicity within the body by being metabolized in the liver to become something known as phosgene, a carbonyl dichloride, COCl2, which damages the body's defense against toxins. So chloroform, trichloromethane, shown here, gets metabolized into this, and that is going to cause the real damage. So that's where this escalates the situation. Now, chlorofluorocarbons, also known as CFCs. CFCs are compounds that contain both fluorine and chlorine atoms. Now, these are chemically inert with most substances. They have low boiling points and at room temperature, they have low boiling points at room temperature and are insoluble in water. They are ideal propellants in aerosol cans. So what that means is if you get something like, not Windex necessarily, but a hairspray or something like that. If you had a chlorofluorocarbon in there, that's going to be very effective at getting that hairspray to spray out. Now, their reactivity, however, with the ozone layer results in depletion of the ozone layer. So their reactivity with ozone, which is a molecule with a formula of O3, and if you think about going to outer space, you've got to go through the ozone layer, and that's a bunch of O3. That O3 reacts with CFCs, or chlorofluorocarbons, plus CFCs. I'm going to say equals less O3, which means your ozone layer, that was a protective layer outside of the Earth that blocked UV rays, gets depleted because the amount of O3 reduces. Now, fluorinated compounds can be used in medical applications. For example, perfluorocarbons can be used as blood extenders and promote oxygen delivery to cells. So perfluorocarbons are capable of doing that. The next and last group of, or the next and last functional groups that I want to talk about are alcohols. Now, alcohols are organic compounds that have a group known as a hydroxyl group, OH. Now, alcohols can have one or more hydroxyl group bound to the organic molecule. Alcohols are known to hydrogen bond with one another. Okay. Now, one important thing about this is that these are organic compounds. So what does an organic compound have? It's got carbon. So basically your simplest organic compound is this right here, methanol, which is CH3 OH. It is a carbon-oxygen bond. This oxygen has lone pairs of electrons. That oxygen, by having those lone pairs of electrons, will love to find out where there's another CH3OH and form a hydrogen bond with that hydrogen. Ethanol is another compound that has H3C, CH2OH. 1-propanol is 1, 2, 3 carbons and OH. Glycerol, well, that's got 1, 2, 3 hydroxyl groups. So alcohol, when you think about it in everyday life, like if beer, for example, has ethanol. That is the alcohol that is produced by yeast, the microorganism yeast that your body metabolizes. And it's going to take that alcohol and convert it and, well, break it down so you can get a small amount of energy from it. This is also something that at a very high concentration could be hazardous. But anything with an OH and carbon is an alcohol, has an alcohol functional group. Now, one of the things that's important to know about alcohols and organic nomenclature is just because something has one hydroxyl group, you do have to assess everything else that that molecule has. If a molecule or a compound has one hydroxyl group, it doesn't necessarily mean that that alcohol is going to dictate the name. There might be another functional group that, and a more abundant functional group that causes or that it is more accurately going to give the name. Okay. Well, I broke this into two different presentations because what I want you to do is take some time with this. Be careful, or like work through this slowly. Watch this slowly, scrub back. Try to come up with names for compounds. Like if you were to come up with a 5-carbon molecule with an OH group, I could draw it. And remember, each one of these points would be a carbon. So here I've got 1, 2, and then 3, 4, 5 OH. So that's 1, 2, 3, 4, 5 hydroxyl. So this would be pentanol. 5 carbons, 1 OH group. So try to think about what those names are. Now, this right here, T-butanol, that has 1, 2, 3, 4 carbons. Hence, it is bute. It's also an OH, so that would be butanol. Now, this has these carbons positioned and organized to basically give this T-shaped structure, which is why it is T-butanol. Okay. This is all the important stuff about alcohols and your basic intro into functional groups. I hope this was helpful. And remember, on Friday, we're going to have a review session. So I'll be working through some practice problems, giving you some kind of example questions to look for in preparation for your exam. All right, everybody. I hope you have a good one.